Let's talk a little bit more about the criterion of selecting the best model. Um, so basically, um, well, previously we learned how do we do the selection, like best subset selection, stepwise selection, including forward and backward. But now in this small section, I want to get a little bit more of why we're making the selections as that, why we're using the criterion we're using, and yeah, just a little bit more of theory behind it. Um, so we have mentioned it several times. Um, well, we could use our residual sum square RSS or R square to compare um, models of the same size. Same size means have the same number of predictors. So, and the model containing all the predictors will always have the smallest RSS and the largest R square. Okay. Um, and well, we actually want to avoid overfitting. Like overfitting means you put too many predictors in the model. We want to avoid overfitting and want to get good prediction accuracy on new data. So using like RSS and R square are not really suitable for that, especially if you're doing that on your training data set. Okay, we have two options here to overcome that problem. We could either indirectly estimate the test error by making some adjustments to the training model error. That is to account for the bias from overfitting. Okay, we still use the training model, like we evaluate on the training model, but we do some adjustment on it to try to use that as an estimate for the testing error. Okay, or we can directly estimate the test error by just split it to our training and testing data. That is our validation set method, or we do cross-validation, right? To cross-validation, that way like k-folds, we do our modeling on the training part and also testing on our validation set. Okay, but the variable selection here in this chapter, we're actually estimating the testing error by running the models on the training data, that we do some adjustment on the RSS, like on the criteria. So, well, if you still remember, we used this mean squared error to kind of quantify how well like the model fits, and um, and we know that this mean square error is generally an underestimate of the testing mean square error. Okay, the model mean square, and when you do it on the training data set, it will be underestimate the testing data set mean square error. And we know that mean square error is just the residual sum of square divided by sample size n. Okay, so this is sort of related. So because this mean square error is underestimating this testing mean square error, so we try to do the adjustment that we could to overcome this underestimation. Okay, and why it's underestimate? Let's talk a little bit about it. It's because when we fit the model, well, using least square, we actually specifically estimate the regression coefficients to make the training residual sum square as small as possible. Okay, like remember when we do the fitting, we try to get the points, or we could see we try to put the line as close as to the data overall. That means the error like the residuals trying to be as small as possible so that all the data points like kind of equally spread out around this line. Okay, we try to make the coefficients so that the residual sum square is small as possible. Okay, so that's on the training data. So, well, this is directly related. On the training data, we try to make it the RSS small so that the mean square error for the training data will be small. That's comparing to the true testing mean square error. That's why it's underestimated. And the techniques we do for the adjustment on this residual sum square are actually the criteria that we just talked about in our selection, which is CP and AIC, BIC, and this adjusted R square. Okay, and this is the full name of the AIC and the full name of BIC. Let's take a look at them individually. So here I basically get the information from the book. Like for the CP, we're doing a fitted least square model with D predictors. Okay, under this notation, we have D predictors, and the estimate like adjusted version of this RSS is this CP. Is like this, and sigma hat square is the estimate of the variance of the error terms. Well, typically it's from the full model. That's the error term from the full model. And what is this doing is just adding a penalty term. I mentioned there is a price to pay when you include more variables into your model. And this penalty term is to adjust for this underestimation of the test error. And also you can tell this penalty term would increase as the number of predictor increase. So the larger D, the larger this term will be, right? And we know when we increase the number of predictors, the residual sum square, this term will decrease. So this one will go up, this one will go down. It's a trade-off between these two, right? And when it's at the right place, at the right number of predictors you should include in your model, then you will achieve the lowest CP. So this is an unbiased estimator. So this CP is unbiased estimator for testing mean square error. So similarly as when we choose model according to mean square error or residual sum square error, residual sum of square, we want to choose the one with the lowest error, right? So it's the lowest CP. Okay. And the next one is AIC. And well, this one, comparing to CP, it can be used for relatively large number of models fit by maximum likelihood. And for the least square models, this AIC is defined as this. So, it's not the exact like equal. There is actually additional constant behind this, but because it's a constant when we compare into models, we can just ignore that part. We're only comparing this changing part. Okay. So for these square models, AIC is proportional to this CP. So this criteria will just follow the same pattern as CP. So they are very similar. But this AIC can be used for a large number of models. Okay, this is AIC, and then let's look at BIC. So this BIC is derived from Bayesian statistics. And that's why it got the name, like Bayesian information criterion or something like that, but ends up being very similar to the previous two criterion. again, with the least square model with D predictors. D is a number of predictors, and the BIC is defined as this. So you notice the constant 2 becomes log n. And so this one, yeah, again, this one we will want the smaller BIC, the better. And we replace this 2 by this log n, because this log n greater than 2 for n when you have n greater than 7. So BIC is putting a larger penalty on the models with more than 7 variables. So when you have like many variables, it definitely put a larger penalty on the models. And so BIC will tend to select a smaller model compared to AIC and CP. Okay. The last one is the adjusted R-square. And we used this value previously. It's the same as before. So the definition will be the same as before. And unlike it's not like the other 3 criteria. We would want to maximize adjusted R-square, which is similar to how we want to maximize R-square, right? And the intuition behind this is here. So maximizing adjusted R-square is the same as minimizing the residual sum square over the degree freedom n minus d minus 1. And once the correct variables are in the model, if we add additional noise variable, like those nonsense variable, it will only raise the residual sum square a very small amount. So this raise will be offset by the increase in D. And that would lead to an increase in this RSS over n minus d minus 1. Okay, so this is the intuition behind this ratio. Why we like the trade-off? How is the trade-off happen? Okay, that's the adjusted R-square. And okay, let's take a look. Some conclusion about those criteria. The basic idea, they all have like the same background. So the value of the criterion pays a price for the inclusion of unnecessary variables, okay? And minimizing or maximizing, like the adjusted R-square, will increase, minimizing or maximizing this criterion will ensure that only the correct variables will be included. If you add any like unnecessary variable, it would actually drag your criterion to less preferable, because we already mentioned like how the trade-off will happen. And this is basically how we could use the criterion to select the correct model, the best model, select the correct variables included in the model. Typically, I would suggest you look at all the criterion when you making a model selection or variable selection. If like the number of variables you are choosing, it's among 4, 5, and 6. So it would depend on the goal of your study. If you want to get better prediction accuracy, you can use relatively higher number of variables. So in this case, we would use 6. But if you want to get better interpretation, then you want to get a simpler model. So maybe you can use the one with 4 variables. So in terms of this like variable selection, there is some outcome result happening here. So this is just like the law of parsimonies or something like that. So which basically means the simple, the better in terms of the model selection. Most of the case. So, well, the theory behind this criterions, actually, there are some very rigorous proof about their theoretical justifications, though the adjusted R-square is less so than the other three criterion, like AIC, BIC, and CP. Yeah, in Schiller book, that book touched on the theory, but that is mostly beyond the scope of our class. Okay, if you're interested in those theoretical proofs, justifications, you can definitely go take a look. Yeah. Okay, that conclude the material for variable selection this week.